Hello, everyone. Welcome to our online electrochemical colloquium series. Thanks for joining, and we have almost 200 participants now. So in the beginning, I would like to make a few announcements. So first of all, I had to put a mute and no video on for everyone until we reach the Q&A session, when you will be able to directly ask your questions. It's also important to say that we will have a 10-minute break in the middle so that you could digest the first part of the talk, and you'll be able to ask some questions. And then after the talk, we will have plenty of time for further questions. So today our speaker is Axel Gross. Axel, he received his PhD, and he actually also a habilitation degree in theoretical physics. And he's currently a professor at Ulm University. He's extremely well known as a leading expert in theoretical surface science, and which is most important, in theoretical electrochemistry. And I would say that most of his studies target the solid-liquid interface, especially the interfaces that are formed with platinum, because platinum is a great modal system or modal metal for a lot of different electrochemical heterogeneous reactions. And so I think that his talk will be able to really be serving as a great starting point for all our colloquiums. So with that, let me pass the microphone to Axel.
Okay, thank you very much, Andrew, for this very nice introduction. I'm really honored to be the first speakers of this series, and I hope this will be a very interesting series. And I thank you very much for all your effort and that you have done in order to initiate this. So let me share my screen. Do you see the slides? Okay.
Yes, we do.
Okay, good. So okay, so the title of my talk is Structure of Electrode-Electrolyte Interfaces from Continuum to First Principles Approaches. And Andrew asked me also to make a kind of tutorial starts, which I'm happy to do. So I will first introduce the challenges in theoretical electrochemistry. I'm in fact more or less a surface scientist by training, and for me, so to say, to treat electrode-electrolyte interfaces is like the new frontier for surface scientists. Then I will briefly discuss traditional continuum description approaches of electrochemical interfaces, and then tell you how we can determine the structure or the coverage of electrochemical interfaces using grand canonical approaches. Then I will switch to the atomistic simulation of electrochemical interfaces, and if time permits, I will have I also have a few slides on electric double layers in batteries. Okay, so in principle, what's electrochemistry? And it's very simple. You can define it, and this definition is from Wolfgang Schmickler. You can define it as that it's concerned with structures and processes at the interface between an electron and an ion conductor. And you all know that electrochemical energy storage and conversion is a very modern topic nowadays. So it's important, for example, for fuel cells, in batteries, electrocatalysis, you have electrochemical interfaces, electrolysis, the production of hydrogen. You can also have photocatalytic water splitting, which is where you want to have like artificial leaves. But there are also processes that you would rather avoid, like corrosion, which also in principle is electrochemical process. And even in life science, at membranes, you have electrochemical processes. But now, what is the challenge in describing electrochemical solid-liquid interfaces from a theoretical point of view? And first of all, if you have a liquid, this means that you can't no longer use the nice tools that you have typically in when you perform atomistic simulation. You push a button, says optimize. Here you have many different structures. So you have these liquid electrolytes require to perform statistical averages. And this also means that instead of total energies, free energies have to be determined, which all is very time consuming and also rather complicated. Second, An important control parameter in electrochemistry is the electrode potential. And so instead of dealing with total charges that we typically do when we perform first principle structure calculation, we have to deal with the constant potential, and which also means that the charge of the electrodes might vary in time when we simulate electrochemical processes. Furthermore, and it's very important, and I guess this is sometimes overlooked, the electrolyte is an ionic conductor. So there need to be ions there, and so they correspond to a reservoir of ions, and the interaction of these ions with the electrodes need to be considered. So as a function of electropotential and concentration, the ions might adsorb at the surface, and this is important in order to really determine the activity and structure of these interfaces. But in principle, it's very easy what we should do. So the appropriate ansatz would just to be, we perform reliable quantum chemistry calculation of these interfaces under potential control. We just need to include an appropriate number of electrode molecules and have to take their statistical nature into account through averaging over sufficiently long ab initio molecular dynamics simulation. So pretty simple, we know what we have to do. But unfortunately, such an approach is currently not possible, and probably will also not be possible for a long time due to numerical obstacles, just due to time, computer time, but also to technical and theoretical, for example, with respect to constant potential simulations. So let's start with the continuum description. And again, I just repeat here that electrochemistry is concerned with the structure and process between an electron conductor and an ion conductor, the electrolyte. And in principle, interesting enough, this is not too far away from a p-n junction in semiconductor physics. You might have a p-doped and an n-doped part. This would then be like the ion conductor. This would then be the electron conductor. You have a potential drop across the interface. You have here some space charge layers, which are resembling the electrical double layer. And also the electrochemical interface has a strong similarity to a Schottky contact, because a Schottky contact is a contact between a metal and a semiconductor. So in effect, if you do a continuum description of these interfaces, they are quite similar. Now here, I show you the typical examples when we discuss electrical double layer. And interesting enough, these pictures have been formed or created more than 100 years ago. First, there was this Helmholtz model already in the 19th century, where there was assumed to be a layer of ions on the surface, and then you would have your linear potential drop. But later, Gu and Chapman mentioned also or pointed to the fact that there might be a diffuse layer. And then Stern combined these two models by having first a kind of ion-like layer and then a diffuse layer. And this is now the famous Gu and Chapman model. And interesting enough, when you hear people talking about electrochemical interfaces, these concepts are still used all the time. And here you have then a more detailed picture of such an electrical double layer, again the Stern layer, and here you have also inner and outer Helmholtz plane, and typically you would solve this with some continuum approach. On the other hand, if you look at atomic sketch, and here I've taken some picture taken from Wikipedia, then you find pictures like this. And here, of course, these balls are just water molecules, and the arrows denote the dipole moment. And then you see here, of course, you have here metal, you have charges inside of the metal, and then you have here the layer. You have cations, you have anions that might specifically absorb. Interestingly enough, the artist who made this sketch all aligned all these water molecules. So is this really true? Are these water molecules aligned or not? And so already here, there already from this artist view, some questions arise with respect to this particular interface. And now here, this picture is taken from a book by Elisabeth Santos and Wolfgang Schmickler, and they have now not really aligned all these water molecules at the metal surfaces. In principle, their motivation was to align them towards this ions you have in solution, but this looks already much more disordered. So there are many open questions. Is the Stern model, which was based on concepts, as I said, raised or 100 years ago, still a realistic model for electrochemical interfaces? Then even this simple question of the exact structure of the water at the electrochemical solid-liquid interface, are they ice-like, ordered, or liquid? I once heard a colleague saying, are they rather soldiers being aligned or civilians very disorganized? Now you see here also you have ions in the electrolyte, which is a typical thing in electrochemistry to consider. And you see also here that the anions absorb specifically, that means their solvation shell breaks, while cations sometimes assume not only to absorb non-specifically. So how do the solvation shells of these ions change at in the vicinity of the interface? Another question. And here you see also, for example, that this ion adsorb is the strength of this, what we call specific absorption electrochemistry, influenced by the presence of this electrolyte, directly or indirectly. And also, what is the microscopic role of the electropotential? When I was first introduced into electrochemistry, I was taught that you might consider something like a temperature, but of course, electropotential is very different to a temperature. So can we get also an understanding for what the role of electropotentials is? Okay, so now let's try to go in a stepwise fashion through these issues. And of course, I won't be able to give final answers to this. I only want to show you, and I want you to kind of repeat also my own way of progressing towards more detailed understanding of structures and processes at electrochemical interfaces. So when I was first introduced to this field like 20 years ago, and people first started to look at metal liquid interfaces, they started with ice-like models. And this is very convenient because if you have an hexagonal surface here like platinum 111, these ice-like layers fit very, very nicely on top of this layers. Also, if you change the lattice constants here by like plus minus 10%, still you often find that these ice-like structures are stable because hydrogen bonds are rather flexible, and you can, to a certain extent, change this bond length, so say. An interesting point also was that in the first decade of the new century, there was a lot of discussion about so-called half-dissociated water layer, where you would have here a water molecule intact, and here you would have an OH group. Now, interesting enough, also, if you just put this bilayer on the surface, there are two modes of doing this, either with the hydrogen atom down or with the hydrogen atom up. And if you calculate the energies, they are often almost degenerate, and it also depends on the particular metal surface, whether this H down structure is stable or H up structure is stable. So energetically and apparently interaction-wise, there's not a big difference between these two structures. Okay, so and when you look at also the influence of the presence of water on the metal surface, you find that there is rather small. What's plotted here are the density of states of the platinum surface. First of all, in this black line is the bare platinum surface, and all the other lines are for water-covered surfaces. And you see the largest change is if you just have one single water monomer, which is strongly bound. But for all the other structures, you see here that the peak height changes a little bit, but no peak shifts. So in principle, this already tells you that there is a rather weak interaction of these water molecules with these metal surfaces, which should then also be true if you have a more liquid-like metal surface. We will come to this later in the talk. Now, but the interesting point is, of course, if you look at these two bilayers, they, of course, have a very different dipole moment. Every second water molecule is flat, so there should not be any dipole moment with respect to the surface normal, but these dipole moments of the H down and H up water layers with respect to the surface, of course, are very much different. And again, you see here, these are the adsorption energies. They only differ with respect to the free water molecule by something like 30 millielectron volt, but the work function differs by 2 eV. And I have to remind you that the stability window of water is only 1.23 volts. So this difference is larger than the stability window of water. And we will also later come to this point that you can derive from the work functions the electropotentials. And so there must be something, these are huge changes in electrochemistry to change the work function by 2 eV. Also interesting point is that naively you would expect, due to the low interaction, that the one orientation would lower the work function and the other one would increase this. But overall, there is a lowering and then there's a change. So there's in fact an interesting point. And in order to find out what's going on there, we determined the so-called charge density difference. So what's plotted here, this is now averaged over the whole slab, so perpendicular to the surface, is the change of the electronic charge density upon interacting the system. So you calculate the density of the interacting system and calculate the densities of the system without the other partner presence. And what you find in both cases, and this is very interesting, is that either for the H down structure or the H up structure, there is a rather strong polarization, and there's a charge transfer from the water molecule towards the surface. Again, this is a very strong effect, but it seems to be rather electrostatic because, as I showed you before, as far as the density of states is concerned of the platinum surface, there's not such a strong change. So this is not clear. Is it a strong interaction or is it a weak interaction? Okay, but now, of course, such water layers on surfaces were also measured in surface science experiments. So you would deposit a layer of water in a UHV chamber, on an ultra-high vacuum chamber, and would measure the work function change. And here you find the results for gold, platinum, and ruthenium as far as the work function change is concerned. And here you see the calculated work function changes for the H down water layer and the H up water bilayer. And you see a huge deviation. And of course, and I might stress this point, if you perform DFT calculation, you always have to be humble and careful because of all the errors that can occur, for example, due to its choice of the functional. But typically, work functions are rather reliable, and you'd never have an error of 1 eV in the work function change. So what's going on there? And so what I will show you now here are plots of initial molecular dynamics simulations of these water bilayers. And you see, we started the simulation with this ice-like, the perfect ice-like layer. And after 1.5 picoseconds, you already see that this perfect hexagonal structure is kind of, is not that strict anymore. But then after something like 8 picoseconds, you see that this hexagonal structure is broken up fully. Now, when we come to platinum 111, you see also after 1.5 picoseconds hexagonal structure. Interestingly enough, you still see this hexagonal structure after 7.5 picoseconds. But if you look at the orientation of the water molecules, what you find is that there's no true H up or H down simulation anymore, structure anymore. And this is here all combined. And I have to admit also that at this time, you see the simulation were more than 10 years old. We performed the simulation in a rather small unit cell. So we had a 2 times square root 3 times 2 times square root 3 structure, and this might already impose that still this hexagonal structure is present there. But you already see for silver and gold, for the weakly interacting system, there's no hexagonal structure anymore left, also for this palladium and gold structure and so on. Interestingly, only for this half dissociated layer, there is still a perfect structure, which is just due to the fact that this hydroxyl atoms or molecules are kind of pinned to the surface, and they kind of pin then also the water structure. And now what I plot here is also the evolution of the work function change for a water layer on ruthenium compared to the experiment. And this bar here represents the 2 results that you can take from these references with respect to the work function change. And you see, interestingly enough, we started with the H down water bilayer, H up water bilayer, but after 2 to 4 picoseconds, in fact, the water layer forgot whether it initially was H down or H up, and then at the end it trails kind of the experimental results. And so after doing this thermal averaging, you then now get a good agreement between theory and experiments. And this is then also plotted for other systems. So if you do the ab initio molecular dynamics simulation, and then you get results of the work function, average results, which are much closer to the experiments. And in fact, this gives a strong evidence that even in this situation, and I have to remind you that these experiments were done at low temperatures at UHV, and where typically water would dissolve at something like 160, 170 K. Already there, the water layer is apparently disordered, because otherwise we would not get this good agreement with respect to the work function. So water at finite temperatures definitely is not ordered, but rather forms a disordered structure due to the weak interaction of the metal surfaces with the water layers. Now, what I want to show you now is one of the trajectories that we also did at that time. And what you see here is a hydrogen molecule. We wanted to model some electrochemical reaction, and you see it dissociates here now. And please follow this hydrogen atom here. And you see how quickly it moves below the water layer, as if the water molecules above are not present. So this is also an indication that often the interaction of adsorbates, like here the hydrogen atom, with the metal surface is hardly influenced by the presence of the water layer. And interestingly, the other one stays here and ends up at the top side, so to say. So this already tells you also that the water molecules sometimes hardly influence the absorption of atoms and molecules on the surfaces. And here you again see a snapshot of a simulation of a water layer. As we started, we had just 2 water layers on a platinum-101 surface. And I tell you in this short anecdote, when I presented this picture to one of my colleagues, the late Professor Kolb, he said, what you're showing has nothing to do with electrochemistry. And I was wondering what he meant. And in fact, what he meant was, what we should have done is the following. We should have performed simulations like that. If you have a platinum surface at low electrode potentials, then it's almost always covered by hydrogen. And you already see with the naked eye that if you have here the hydrogen layer on top of the surface, that now the water layer is kind of shifted away from the surface, and about 1 angstroms, which if you would use a kind of semiconductor language, you would say you passivate the surface and even make the interaction weaker. And this is one of the main messages also of this talk. Whenever you look at electrochemical solid-liquid interfaces, you better make sure that you know the right structure of the interface as far as the coverage of anions and cations on the surface is concerned. And here, of course, whenever you have a surface, you have protons there, which are their concentrations given by the pH value, and you will have a layer on the surface. But now, how can you determine such a structure? Because this is kind of an equilibrium structure. So what are the tools? And so, of course, what you would need is a thermodynamic description. And what you see here is a slide explaining the so-called ab initio thermodynamics model, which is more or less a combination of atomistic simulations and a grand canonical approach. So this is done for oxidation catalysis, and I start with this because it's conceptually easier. So you assume you have a gas phase, and you have here a catalyst surface, and then you have here an interface region. And you want to determine what is the structure of this interface at a given temperature and pressure. And in fact, of course, what you have to do then is determine free energies. So you have to determine the free energy difference between these particles in the gas phase and these particles adsorbed at the surface. Now, typically, what one finds is that entropy effects for the adsorbates are rather small. So that's why this free energy of adsorption often can be approximated by this expression here, where instead of the free adsorption energy here, we just take the total energy, which can be calculated by DFT calculation. And Carsten Reuter made a good job in showing that this is a good approximation. So in principle, now the whole dependence of the structure on the temperature and pressure in heterogeneous catalysis, for example, depends on the reservoir, on the chemical potential of the species in the gas phase. And for example, for oxygen, you could derive this value. And thus, you can now derive structures at surfaces which are equilibrium structure as a given temperature and pressure, which is a very nice tool. Now in electrochemistry, you have a problem there because you have their reference state. Your reference state is no longer the molecule or the atom in gas phase, but it's the solvated species, which is much harder to calculate. But there was now the very nice idea of Jens Nørskov, and the way out is just to realize that at the so-called standard conditions, which in fact define the zero of the electropotential at the standard hydrogen electrode at pH 0, 1 bar and room temperature, there's equilibrium between the hydrogen molecule and the proton in solution. In fact, this is the definition of the zero of this hydrogen potential. Now you might say, aha, this is a strange condition, there's a specific condition, but what is if we change the electropotential? But we know pretty well how these the chemical potentials change as a function of potential and also concentration, which is given here. So we in fact know how we change it, so we can now express the electrochemical potential of the proton in solution by this expression here, where we have as a reference state the electrochemical potential of hydrogen in the gas phase, and then here these are the terms that describe the change of the electrochemical potential as a function of electropotential, temperature, and concentration of pH. And this, in fact, works for any redox couple where we have a kind of equilibrium between a gas phase species and a solvated species. And I illustrate this here. You can also find this in this recent short review here. So in ab initio thermodynamics, you have this three parts. You have here the solid, you have here the gas phase and the interface region. You assume that you have equilibrium all around. And then from here, you describe this in a grand canonical sense with the electrochemical potential, and then can determine the absorption energies here at the surface. In the computation hydrogen electrode, so in principle, you may have now another equilibrium between the electrolyte and the gas phase. And then at the end, you can still all refer to the gas phase, but you can also then introduce the electropotential and the activity or concentration of these particles. And I must make one point here, which is also stressed in this paper. This is all what the computation hydrogen electrode says, nothing else. And so when often people say in a thermodynamical sense, this is fully correct, and all the errors come from the approximation you have to do in order, for example, to calculate here the energy of the structures. That's an interface. And here again, you see this first equation that I already showed you before, which is valid for the electrochemical potential of protons. But now, for example, and we will talk about chloride in a moment. So for chloride, you just look up a table, you find that the equilibrium standard chlorine electropotential is 1.36 volts. And then you can also derive now here the electrochemical potential of chloride anions in solution with respect to chlorine gas, and here the electrochemical potential, and again, constant temperature, and here now the activity coefficient. And then from that, you can also derive free energies of absorption, and I will show you examples in the coming slides. And so what do you do now in order to determine energy structures? And let's first look at chlorine and copper 111. And you see here, this is an example where there was a very small concentration of chloride anions, only 10 millimolar. But even if it's 10 millimolar, you already find this densely covered surface. Within this, the coverage is 1/3, and you have the square root 3 times square root 3 structure on the surface. So this is due to the strong interaction of chloride with copper surfaces. And of course, you can imagine that it's a huge difference whether you have a clean copper surface or chloride covered surface. Now, how do we want to address the structure? So in principle, what we do, and we did this for these highlights here, you first calculate the absorption energies of these halides, or better to say halogen atoms at the surface. One important point also is it's like a nomenclature. Are these adsorbed atoms halogens or halides? Are they ions or atoms? And this doesn't matter. This is just a matter of nomenclature, because once these anions adsorb at the surface, they are coupled to the electron sea of the metals. They have in principle an infinite reservoir of electrons where the electrochemical potential of the electrons given is by the Fermi energy. So it doesn't matter whether they were originally ions or atoms. This is not crucial for their structure. And so then you can calculate all these energies. First of all, you see here, in this particular structure work, we didn't take into account any presence of water. Why is that? For example, you see here this picture. If you, for example, consider this densely packed chlorine layers, you find that the water layers are really floating above this chloride layer. There's weak interaction. So it's, in fact, you might really neglect the influence of this water layers, which is, of course, very convenient. And then what you find is these results. So what's plotted here are the adsorption energies of these halides on this particular surface per halide atom as a function of coverage. And you see the general trend is that that the curves all go to the upper right, which means the adsorption energies become less negative. That means adsorption becomes less favorable for higher coverages, and which is kind of easy to explain because there's a repulsion between these adsorbates. And everything else I will show you now in the next slides is all derived just from these data. But of course, you can't from this data directly derive what is the stable structure, but it's all included there. And then you just apply these formulas that is given here. You just apply this formula, and then you can calculate the structure, and you can even calculate the structure for more than one species. So this whole procedure also works if you do not only include chloride, but also hydrogen. Now, then the only problem is that you have now two-dimensional structures, and every particular surface structure now represents a plane or a hyperplane in this space, and then you have to look at the most stable structure. And if you do this, you get something like this. What we have done is we have calculated the energies of many, many different structures, have applied this formula before, and then you find here the stable structure as a function of chloride electrochemical potential and hydrogen electrochemical potential. Now, of course, the problem is in the experiments, no experimentalist would say, this is my electrochemical potential. You would rather change the electropotential. But this is not a problem. This is all included, this information here. For example, if you, for a given concentration, change the electropotential, you would go along this line. And if you do this, you get the curves like this. And you find here, so to say here, that if you, at low electrode potentials, you would have a hydrogen-covered surface. This is here. And at higher potentials, you would then have a chloride-covered surface. And the interesting point is, there's no area where there's a uncovered surface, which is called competitive character. Here at this particular point, at this electropotential, hydrogen is replaced by chloride, which is in nice agreement with experimental observation. And you can even put this into something that the experimentalists also can directly compare with their experiments in a so-called Pourbaix diagram, where you now plot the stable phases as a function of pH and electropotential. And this can, again, as I said, directly be compared. Again, you see here that at this point, you have a hydrogen-covered surface, and then directly here, if you increase the electrode potential, it becomes chloride-covered. Now, in this particular simulations, we neglected the influence of the water at all. So this were just calculations, in principle, done at the vacuum interface. Now I will come to an example where it matters to include the water, and we in fact needed to include both explicit water and also implicit water molecules, which means we described also the water by an dielectricum, which is kind of plotted here. I will come to this point later and mention this again. So where in principle you just average, you introduce a dielectric continuum, and with a certain permittivity, which is related to the charge density here at the interface. And the system we looked at were sulfate and bisulfate layers at the surface. Now, in contrast to the chloride, these are larger molecules, and of course, they also stand in a kind of upright fashion here. And here, it's in principle no longer possible to neglect the influence of water molecules. But when we first only included implicit water, so a continuum description with no directional bonding, we couldn't reproduce the experimental results. So what we had to do was to include a particular number of explicit water molecules. And I talk you through this picture. So here we have now again this typical rows of sulfate anions at the opposite surface. And then you have here a row of water molecules that are locked in and that kind of bind between or connect these two layers. And in principle, these water molecules are no longer liquid molecules. They are strongly adsorbed and they are fixed here. And then on top of this, we also then included implicit water. And what we then got were these phase diagrams here. And so again, we have here different structures now at the function of electrochemical potential of sulfate and of the height of the protons. And we have done this for platinum and gold 111. Again, you need to compare, sorry, with experiments. Sorry about that. And then you find here these Pourbaix diagrams. And even the interesting point is here that this is almost in quantitative agreement. Even this change of the slope here is in agreement with the experiment. Okay, now this concludes my first part. Let me just have a break for 1 second so that I can kind of get my throat free, and then I will be happy to answer any questions. So please go ahead and ask your question.
Okay, at this point, I will unmute the audience. So please, 1 second. Please ask one by one. So try not to be too competitive in your questions. So we have about maybe 10 minutes for questions, and then we'll be able to continue.
Hello, I have a short question.
Hello, yeah, please go ahead.
How do you measure the work function of a metal that's immersed in water?
Oh, okay, yeah. The model is in principle that the work function you have to determine is the work function of a ion-free water layer on top of the metal. So in principle, you have a finite water layer, and then you have to a vacuum region. So you're fully right, you need a vacuum region in order to calculate a work function. You can't do it in the liquid. But in principle, what you need, according to the model of Trasati, you have to determine, as I just said, the work function in vacuum. And this is also, I will show you this in the coming slides, and this is exactly as we have done this.
But I was wondering, how do they do the experiments?
Or the experiments you see, this were surface science experiments. This were no electrochemical experiments. This were really done in a UHV chamber. They deposited an amount of water and then could measure the work function change. So this is not really electrochemistry, but in principle still surface science. And in surface science, measuring work functions is a general tool, or how they what they can measure.
Okay, yeah, because you need vacuum, right? So
that's right. That's right. No, this were UHV, and as I also mentioned, in the UHV experiments, water already typically dissolves at 160, 170 K. So this is still at very low temperatures. You have to run this experiment at 140 K or so.
Okay, thanks.
Any more questions?
Hello.
Hello.
I am from Max Planck Colon Fortune. I have a very short question regarding the reference electrode value. During the calculation of the constant potential approach, sometimes we use the value like -4.28 to -4.4 EV for setting the reference. So how one can take the exact or reliable reference electrode potential value to calculate the work function or any kind of potential?
Okay, I mean, you're right. You refer to the problem, how can we derive from the work function the electrode potential?
Yes.
And these are these famous, whether it's 4.44 or 4.92 volts. In principle, we just have to take a number. There's no way from our simulations, as far as I understand, where we can say this is the right number. So we only have to be consistent and maybe kind of compare this to experiments. But there's a very intense discussion about this particular point. And I must admit, or at least maybe I'm not competent enough to this, I do not see a way how we can define it. I mean, of course, we can, in theory, we can define it pretty well. And so typically what we have done, and this will be in the second part of my talk, we have typically taken this 4.92 volts as the reference. But I mean, of course, what we can plot and what is kind of an well-defined value is the work function and the electrode potential with respect to the vacuum level. And then the only question, and this is in principle a question that we have to give back to the experimentalist, what is the zero of the standard hydrogen electrode with respect to the vacuum level?
Okay.
Sorry that I can't give you a better answer.
Can I, at this point, I will ask a question from the chat. So Hank Ren is asking if the water ice-like structure changes and how it changes when the electrode potential or the electrode itself, the surface, moves away from the potential zero charge.
Okay. In fact, I didn't take this. I don't have this slide anymore. In principle, if you can apply an electric field, you would be able to switch these layers. But typically, these ice-like layers, they are the wrong subject to ask this question, because when we discuss this electrochemical question, then we will have liquid water layers. And and I will in fact also show slides at the end of my talk. So as I just said, these bilayer models were very convenient models, but they are not realistic in order to describe electrochemical interfaces. But the energy, of course, also depends on the function. As I said, in fact, I took this slide out 3 hours before my talk because I have too many slides anyways. One can show that the stability then depends on the applied field. And this, for example, has been also used in STM experiments where you flipped water hexamers as a function of electric field. Is this answer sufficient, or?
Yeah, I guess.
Andrew, you don't know.
And then the related question is how the arrangement of water molecules can be correlated with the I guess electrocatalytic activity of particular metals. So if you extend this discussion of the surface under the potential in liquids a bit further into the bond breaking reaction, so can the structures that you're simulating, do they have any effect on the electrocatalysis?
Okay. I mean, you see, this will be not a talk on catalysis. Of course, I mean, I will mention catalysis. I mean, first of all, of course, electropotential changes also typically the charge state of the surfaces. And I will also show at the end that, for example, if you are at high electrode potentials, typically you have a more positive surface, which attracts, for example, also the oxygen atoms, which are typically negatively charged, and so on. So you can also have the simple concepts with respect to the orientation. Now, how the catalytic activity depends on the electropotential is a very, very interesting question. And this has to go deep into the electronic structure. And as far as I guess, there is not a real answer yet to this. So I at least can't. I mean, I would just say it depends on the particular reaction. I think there are no simple rules. So there are simple rules what you have on the surface. So typically you can say when you have low electrode potentials, then typically the surface, the electrode is negatively charged and you absorb cations. When you have high electrode potential, the surface is typically positively charged, so you attract anions. And then it depends on the reaction, which kind of species you want to absorb. And then you find that this is then related to this. But as far as, for example, breaking bonds are concerned, this is, I think, a much more complicated issue. And there are, to the best of my knowledge, no real systematic studies yet.
Any other questions before we continue?
Sorry.
Okay, maybe we shall we continue?
Okay, yeah, I'm sorry that's already take up some time. Okay, so let's go back to my question mark, my nice question mark. Okay, so now what I will kind of change gears a little bit and now talk about optimistic models of metal water interfaces. And first of all, whenever you do calculations with the DFT, you better make sure that you have the right functional. Now, for the experts, since we are interested in metal surfaces, we need so-called GGA functionals, so of this PBE family, and we also need to take into account dispersion effects, because only with dispersion effects you get right water structure. And we made careful studies, so we calculated water cluster, ice-like structures, and also determined the liquid water properties, and found out that this particular functional, RPBED3, is a very good functional, not only to describe water properties, but in fact also to describe the. So this is then the functional that we used in the following. And now what you see here already is a kind of, if you wish, a brute force simulation. So this is a ab initio molecular dynamics simulation of water layer on a platinum slab. And in fact, we had a 6x6 surface unit cell, and we had about 6 water layers. And so we had in total per simulation cell 144 water molecules. And as far as I have followed the literature yet, nobody else has yet done such a structure yet. And I want to express 2 things here now. So first of all, now for this water film, and this relates to the question, we can now calculate the work function here in the vacuum region. This vacuum region, you see, it's about 1.5 nanometers. So typically this is sufficient to have a flat region. And so what you plotted here is the work function along the run. And you see here this value of this work function, which is given with respect to the vacuum level. So there's now no particular, it's not this the standard hydrogen electrode potential anymore. You also see here fluctuations. Also, what I want to stress here is that you here see the so-called 1 electron potential, and also the change of the 1 electron potential compared to the vacuum film. And here what you see also in this structure here is that you do not see this kind of smooth decay, which you saw in this Gould-Chapman model. You see already oscillations. So the layered structure of water, at least in this first layer, is reflected also in this kind of 1 electron potential. And this already tells you that the simple-minded picture of the Gould-Chapman of the Stern model is not really appropriate. Another point what I want to make is here, before we performed also simulations in a 3x3 surface unit cell, so with a much smaller number of water molecules. And what you see here is now along this run of 40 picoseconds, the work function in the 3x3 cell in blue and in the 6x6 cell in red. And you see very interesting here you see also distribution, that the distribution is much narrower the larger the unit cell is. And in fact, this is also important for fundamental understanding. If we were able to run this simulation, let's say at the 1000 by 1000 cell, we would have more or less a very narrow distribution here. So the smaller the cell, the larger the variations. In fact, this has been used by some colleagues when applying the so-called generalized computation hydrogen electrode, because in principle you can take all the bins here, or all the 4 different electropotentials. Of course, you might argue that in the smaller cell here, you could have structures which would be also present locally in a larger cell. So there's still a kind of open question. Shall you kind of average here this work function, or shall you just take every single point for a different electropotential situation? And I would rather still use the kind of mean value, because they might be all parts of a larger ensemble when looking at the larger unit cells. Okay, so now what we also then determined, or what we asked ourselves, is the question: how liquid-like are these water layers on front of a metal surface? And also what we did is we did different calculation. What is called here PCC is the point of zero charge. This were just clean water layer, no other atom in the cell. But we also performed simulations where we added here a hydrogen layer here, which is this, we had 36 hydrogen atoms adsorbed per unit cell, or where we also either took away or added some hydrogen atom into the surface unit cell. And here this is called this trajectory 2H3O+, but this is still an electrostatically neutral cell, because we just, what we did just here, we took away hydrogen, and then the electron would then move to the Fermi energy of the platinum surface, and it would leave here this hydronium ions in the or when we added the hydrogen atom, it would leave the hydronium cation in the water. And but here what I want to stress here is that first of all, you see here this, what's plotted here is the oxygen distribution for these different layers. You always see here a first peak, and in principle this peak, in my opinion, has nothing or only little to do with particular binding. You just have here a flat stage, if you wish, and then you will always find a kind of peak structure here, because the molecules here will have to align with respect to the surface. But the interesting point is that already here from the second layer on, you rather get a flat distribution. So in principle, the water already becomes rather liquid-like from the second layer on. Now what you point here, and I'm sorry for this table here, is that we had looked at different structures. So here there was no hydrogen, there was a pure water layer, and here we added one hydrogen atom, we took away one hydrogen atom, we had one adsorbed hydrogen atom, we had adsorbed OH group, we adsorbed 36 hydrogen atoms, and we also added 2 hydrogen atoms, and this always then translates to different work functions, and then translates also into different electropotentials that you see here. And now, of course, you see here that we have taken, in fact, I didn't mention the right number, we took this particular number of 4.44 eV here in order to derive, to change the number from the vacuum, the absolute work function level, to the SHE level. And then what we also did was we analyzed this, and I'm very sorry that this is so small, I don't have a looking glass, but what is plotted here is the following. This is now the clean platinum surface, and I will come to this back in a second. What we find there is that there are certain water molecules that are adsorbed there through the oxygen atom. This is what we call the sole air water molecules. And then we have also a second layer where you have water molecules that are not bound through the oxygen atoms. And these water molecules bound through the oxygen atoms are much closer to the surface. But what's plotted here is the distribution of this particular oxygen atom along the whole run. And you see here also, if we have a peak here, this distribution also reaches out into the water layer. This means nothing else that no water molecule here stayed within this 40 picoseconds at the surface. So this already tells you that this is a very dynamical structure. The water molecules are just not stay in their layer, but they constantly approach the surface, desorb from the surface, and so on. So it's a very dynamical stuff. Now here you see the simulation where we added a hydrogen layer. And so here with the hydrogen layer, now no directly adsorbed water molecules occur. So you hardly find something. You find here 2 water molecules which were bound here, but not as strongly as those. And here then even the change is much more dynamic. So in principle, this tells you that such a water layer on a surface is a very dynamic object, and the water molecules change their positions all the time. And also now, what I mentioned before is this following fact, that if we, for example, here add a hydrogen atom, then the hydrogen atom will transfer this its electron to the surface, and you get a negatively charged surface. And then what's plotted here is the coverage, and then this coverage of these water molecules that are bound to the surface through the oxygen atom is in fact rather low. Here, if we take away a hydrogen atom, then an electron is transferred to the hydronium ion in the solution, and you get a positively charged surface, and this increases then also the coverage of this hydronium of this water molecules directly at the surface. And this is then also, so again here, for higher potential, you have more directly platinum bonded hydrogen molecules in higher structure of water layer. And this is what you also see here in this so-called in this sorry about this, in this heat maps, you see the distribution. So this now corresponds to this lower electrode potential, and you have a more diffuse structure, while here, if you have this the higher electrode potential, you see now that the structure is much more, or that the water molecules are much more localized there, because now you have more higher number of strongly bound water molecules at the surface. And you see that this is really related also to the electropotential. So the higher the electropotential, the more easily the water molecules absorb through their oxygen atoms, and this forms a more structured surface. Of course, you have to take into account in principle also the coverage. But here you see the dependence of the geometry of the water molecules at the surface. Now, in fact, we were not the only ones to do this simulation. So this is also a work by G. Baolet and co-workers, and where they now compared platinum 101 and gold 101. And again, what you see here now for platinum 101, this particular conditions is again these two species of water molecules, directly bonded water molecules and non-directly water molecules. But in effect, for gold, the interaction is much weaker, and on gold 101, you hardly find these directly absorbed water molecules. And also here, this is now the change of the polarization and the change of the electron density of the water molecules. And again, here you see this transfer of electron charge from the absorbed water layer to the region between water and the metal surfaces. And this is what I also showed you with this ice-like water layers. For platinum, you have this strong transfer, which for gold is much weaker. So it's related to the interaction of this water molecule with respect to the surface. Again, also a very recent study where we find exactly the same results here. Also, you find this here, this change, the transfer of electron charge for platinum, and for gold is much weaker. And again, also this oxygen-bound water species is much less prominent on gold 101 than on platinum 111. Now, in this last foils, I also want to address the issue of implicit solvent. Now, I can tell you my PhD supervisors once told me there are two ways of doing simulations. Either you first calculate and then average, or you first average and then you calculate. And why is this relevant here? So in principle, if you would first calculate and then average, you would just take a molecular dynamics run and make, for example, many snapshots, and then you average over the statistical ensemble. Or you could first average. This would mean you replace the explicit water molecule by a dielectric continuum, and then you calculate. And of course, this is much less expensive. And in recent years, this has been become a very popular approach, and it has been implemented in many codes. For example, in the WASP code, the so-called WASP-SOL model by the group of Richard Tanning and by Kieran Matthew. And we also use this in order to address the methanol oxidation on a platinum surface. And what's shown here, and this is, so to say, first or it's the first step of the methanol oxidation. And what we were looking at was the first dehydrogenation step of methanol on this surface. And there are two options. You can either break this OH bond, and then you have the dissociation into methoxy and adsorb hydrogen atom, or you can break an CH bond, and then you have methoxy hydroxymethylane and the adsorb hydrogen atom. And what's plotted here are the reaction curves, the minimum energy path along this reaction. First of all, for this OH bond breaking, and in blue for the CH bond breaking. And you see two curves. The dashed line is the line in vacuum, and the solid line is the line in the presence of the implicit solvent. Now, first of all, you see that the full lines are below the dashed lines, which is just simply the stabilization of the methanol and the species along this reaction path. But the interesting enough is that you see here, in this case of the CH bond breaking, these two lines are more or less, to a certain extent, parallel to each other. While for this other, the OH bond breaking, the difference really becomes smaller and smaller. And why is that? Simply because here you break the hydrophilic OH bond. And so here, this species doesn't longer have a hydrophilic CH bond anymore, while this is still intact. So here you lose the stabilization of the species. And this, in fact, also leads to the fact that the barrier for this process is increased in the presence of implicit solvent, while here it's in principle it's reduced or so. And this is in a very nice agreement with the experiments. You find that at the gas-solid interface, the CO bond, the OH bond breaking is favored, while in the presence of water, the CH bond breaking is favored. And we also looked at this then for other species. So we looked now at the stabilization of adsorbed species, and we looked always at isomers, which either have an hydrophilic OH bond or not. In all cases, the species with the hydrophilic group is stabilized. And I mean, this might be related to the question what for example, the presence of water does. So of course, it stabilizes reaction intermediates or reaction products which are hydrophilic. But of course, this is qualitatively very nice and it makes sense. And of course, you would have guessed it before. And it's nice that it gives the right results, but is it quantitatively correct? And in fact, there's a very nice work of the group of Karen Chan, where they, in fact, compared adsorption energy in implicit and explicit solvent. And I don't want to go through all these details. So they looked at different copper and platinum gold surface. And what's plotted here, and you should look at the lower panel. These are the solvation energies, so the adsorption energies in either according to a molecular dynamic simulation, where you have an average, or you have here a certain error bar because it's a statistical average, or you do it in an implicit solvent. And what you see here is at this particular surface, the species are more stabilized in implicit solvent. The red symbols are below the black ones, while here's the other way around. And also across the different surfaces, you find no trend. So you have differences up to 0.6 eV in the solvation energies between implicit and explicit solvent, which very strongly across metals and surface. So there's no general trend. So the unfortunate signal of this is that in principle, there is no general rule. And so in principle, we certainly still have to work on the quality of the implicit solvents because they can be rather unreliable with respect to adsorption energies. And even sometimes qualitatively, you find different trends. Now, if I have now another 5 minutes, I just want to give you one example from a batteries and also the interface, electrochemical interfaces at batteries. And this is just to summarize how a battery operates. And the important point for example, from the lithium-ion battery is that in principle, the process that you look at is not, it's of course, you transfer in the electrolyte a lithium cation, and you have in the outer circuit, you have the electron transfer. But thermodynamically, what you transfer a lithium atom from the anode to the cathode. And that's why we also, with DFT, we can nicely calculate it. This is in principle a free energy change. We can calculate it. And if we divide it by the number of charge carriers that are transferred by this operator, we can calculate the open circuit voltage. And in principle, note that thermodynamically, the basic reaction is not an electrochemical reaction. And I remind you, in thermodynamics, the kind of path that you pursue from the initial to the final state does not matter. So in principle, whether the electron takes a detour or not doesn't matter. Now, I now come to this, to the fact how this open circuit potential can be calculated. And for example, if you now look up this paper of John Goodenough, who just got the Nobel Prize in chemistry, you find pictures like that. And you can just say that you can also then derive this open circuit potential from the difference of the chemical potential of lithium in the anode and the cathode. And then you find pictures like this, where there is also the HOMO-LUMO gap of the electrolyte put on the same scale. And I was very confused by this picture, because which electrochemical potential is meant here? If this is electrochemical potential for the atoms, then you can't directly relate it to the HOMO-LUMO gap. And also I must admit, and this is maybe the lesson learned from this, even Nobel Prize laureates can have wrong concepts, because it's indeed not the HOMO-LUMO gap in the electrolyte that is important for the stability, but it's rather the redox potentials. And the most important, or the very prominent example, is water. Water has a HOMO-LUMO gap of something like 8 EVs, but it has a stability window of only 1.23 EV. So all the statements that you find in the Goodenough papers about the stability of electrolytes, just forget about it. And you can read this in this nice paper here, that this is the misconception that the HOMO-LUMO gap of the electrolyte matters as far as the electrochemical stability is concerned. But still, we want to look at these open circuit voltage again. And of course, in an electrochemical sense, you can then subdivide the chemical potential of the lithium atom into the electrochemical potential of the lithium cation in the electrode. Now let's do a Gedankenexperiment. Let's first disregard the presence of electrolyte and look at the anode and a cathode. And of course, you can determine, if you wish, the insertion energy of the lithium, and you can determine the chemical potential of lithium in the anode and the cathode. And of course, this potential has to be lower, because this has to be the transfer of the lithium atom from the anode to the cathode has to be associated with an energy gain. And of course, I now plotted here some kind of electrochemical levels, but in principle, they don't matter. And I just kind of aligned this with respect to the vacuum level. Now, let's see what happens when the electrolyte is introduced. And what I want to remind you is that an electrolyte is an ion conductor. So in principle now, the lithium plus cations, they can freely move in this ion. And in principle, what you need to have then is an equilibrium of lithium cations. And this is plotted here. So you now introduce here this the electrolyte, and as it's an ion conductor, now the lithium cations can penetrate here, and then they will penetrate here. And of course, after a certain time, there should be thermodynamic equilibrium. And so these two levels have to be aligned. How can they be aligned? Because they were not aligned before. If I just go back, you see they were different here in this initial condition. Now what happens is that there will be electrical double layer formed, and they will exert electrochemical fields, and these fields will lead to the fact that now the levels of the cations, lithium cations, are aligned. Now, of course, you have also the Fermi levels here, but the electrons have the opposite change. Now, these electrical fields here, due to the cations distribution here, they kind of push the two levels together, and it's positively charged. But they will exactly do the opposite. By the same amount, these two levels of the cations are shifted together, the Fermi levels will be shifted apart. And so that at the very end, when you have, so to say, this open charge, open circuit situation, the difference of the electron of the Fermi energies of anode cathode will be exactly the open circuit voltage. So now the whole difference is in this electronic level. And if you now, for example, here close this gap, the first electrons will exactly gain this energy, and this will be exactly the open circuit voltage. So I just mentioned this because it's important that also the electrochemical layers play an important role here in this battery surfaces. And so the open circuit voltage is entirely given by the difference in Fermi energies anode and cathode. Now let me wrap up my talk, and I'm sorry that I talk a little bit longer. So first of all, I want to stress that this is a very nice field. The theoretical study of electrochemical electrode-electrolyte interfaces is, on the one hand side, scientifically very interesting. There are so many questions and challenging, but it's also of high technological relevance in the context of electrochemical energy storage and conversion, renewable energies, and so forth. So this is a very nice field. And I mean, the fact that you're interested in this already tells you that you are that you are aware of this fact. But this field has not matured yet, and particularly with respect to performing first principle simulations under potential control. And I also often like to tell you an anecdote. There was an ACS national meeting like 5-6 years ago. There was a session on theoretical electrochemistry, and there were three talks in a row, including mine, which all started with a 2 watt. Toward a more realistic description of electrolyte interfaces. We are not there yet. There is lots of room in order also to improve the methods, to improve the foundations of the description of the surfaces. And in principle, my observation is that in recent years, there had been fewer attempts to address the potential controls. You find still a lot of papers which mention potential control, but it's typically not the potential control you would think in a kind of grand canonical sense with respect to the DFT calculations. And this approach of the computation hydrogen electrode, where in principle you do not need the potential control with the calculation, has been able to describe or to properly explain many phenomena almost too successfully. And I have the feeling that this has kind of dismotivated colleagues from pursuing this goal of really having the first principles calculations under potential control. But this is a question mark, and this might be open to discussion. Of course, also one important take-home message is really, which the lessons I learned 10 years ago, is that if you perform any theoretical study of electrode interfaces, first, you better consider what is the equilibrium coverage of the electrode. And this is what I mentioned with the hydrogen atoms, also with the chloride, halide atoms on top on the surface. So you might do a calculation on a clean platinum-101 surface, but in principle, platinum surfaces are hardly clean in any electrochemical situation. Either they are hydrogen covered at low electropotentials, or they are OH covered, or covered by other species. Typically, there's only a small window where palladium is not covered. And if you then do simulations only for the clean platinum surfaces, they might be interesting, but they might not be relevant for any experiments. So this, you have to really to make sure that you determine that you look at the potential range your calculations are meant for, and that then you choose the right proper coverage. And also, approaches employing implicit solvent models are becoming increasingly popular, and I've told you that we also ourselves use them because they are computationally very efficient and so on, but their reliability and accuracy is still hard to assess. And I showed you the examples that there are still rather large inaccuracy with respect to the implicit model solvent models. So we certainly have to benchmark these calculations, and we have to find out how reliable this is. And in fact, that's what is also my last point is, there's still certainly a need for numerical demanding ab initio molecular dynamics simulation addressing structures and processes at electrode-electrolyte interfaces to, first of all, also to gain further insights. And of course, for example, I have not mentioned at all electrochemical reactions yet. In principle, what you would also need there is to determine free energies. We would have to determine, we do need thermodynamic integration schemes, which are even more demanding. But we certainly need them because, again, in order to understand things more clearly, but also to have benchmark studies for computational less demanding methods. Now, first of all, so I have very short conclusions now left. And I hope that I've shown you that we can learn insights into electrochemical systems from this first principle electronic structure calculations. Of course, I haven't done this work on my own. I needed funding agency, which are listed here. We needed computer time, and needed also my co-workers, without whom all these studies would have been impossible. And for this particular study, Katrin Forster-Tonigold contributed, Florian did some work, Zhang did quite of work, and Fernanda is not on this picture. That's why I also included her. And so I have to thank this funding agency. I have to thank my co-workers, and I have to thank you for your attention. And of course, please now feel free to ask any questions. Thank you very much for your attention.
Thank you so much, Axel. This is a really great, and I would even say it's very important talk because there are many lessons that I think the audience can learn from it. Let me unmute the audience, and then everyone could ask questions. So I'll let everyone start. Yeah, go ahead.
I have one short question. Could you please comment on the surface wettability? Because I remember one paper from your group over the surface wettability of nickel oxyhydroxide. So in this one,
there are many issues about wettability. In fact, you're talking especially this hydroxide.
Right.
There was also a question already 15 years ago with respect to metal surfaces. You see, wettability in principle is an issue that is important for the accuracy, because whether a surface wets or not tells you whether your DFT calculations are correct. Now, of course, you know when you perform an electrochemical experiments, you do it at room temperature and you have a water layer, and wettability is only an issue if you have small water films. So this is a cheap answer, I must admit, but they are very important as far as the accuracy of your functions are concerned. But with respect to a typical electrochemical experiment where you just have a bulk water there, I think this is not that crucial. Of course, now when it comes to fuel cells, there you sometimes have only water films. But I haven't really answered your question, I guess, yet. I mean, I know we did this study, but I don't have foils available for this particular structure. Do you have one particular question with respect to this nickel hydroxide?
Yeah, my question is, currently we are working on in constant potential approach to calculate the protonation deprotonation side of the surface, particularly for nickel oxyhydroxide or cobalt oxyhydroxide.
Yeah.
But it's very difficult to access the pK value, I mean the protonation deprotonation of the solid structure. So what we are trying to find out the proton dynamics, I mean the dissociation of the water into the proton and hydroxide. But we cannot get any correlation with experimental, and also we don't have any cheap computational method how one can get a correlation between these phenomena with protonation deprotonation along with the oxidation reduction, because we just follow the protonation deprotonation and oxidation reduction separately, not in the computational hydrogen electrode model. And at the same time we are trying to consider this kind of surface wettability to propose a new methodology for oxygen evolution reaction. This is my whole question.
Yeah, I mean, in principle, the computational hydrogen electrode should work to a certain extent. Of course, this is a different issue. This now, nickel hydroxide is a band gap material. For this issue with the band alignment, so this is why typically the computational hydrogen electrode doesn't work that well. It works well for metals because metals expel electric fields, so that's why electric field dependence do not matter. And of course, the hydroxide or oxide surfaces are much more complicated because you have all the dissociation and you have many different surface sites where that can be. So again, I can't give you a simple answer. The only answer is it's much more complicated than the water structure as metal surface due to the fact that your water dissociates very easily and so on. So in fact, we also are starting to look at this again, and we realize the same things. And maybe you should contact me directly, and when we can discuss this issue, just please feel free to contact me via emails. But there's no, I think, no simple answer to this issue. The general answer is it's more complicated as metal surfaces are, and you have to be much more careful also that you find the right structure, because oxide surface or semiconductor surfaces change much more in the presence of water than metal surfaces do.
Okay, thank you. I will contact over the email.
Yeah.
Thank you.
Please feel free to do so.
Thank you.
Any other questions?
Yes, I have a short question. Thank you very much for this really interesting talk. I was just wondering, just to discuss some theory, like the Fermi level of a material is meant as the electrochemical potential of its electrons.
Yeah.
Right?
Yeah.
And I'm just confused with a bit of terminology here. I'm a physicist as well, and at my faculty, we always said the chemical potential of electrons. Is this like the same thing as the electrochemical potential of electrons?
Yeah, you see,
there's confusion here.
Yeah, I mean, I understand your confusion. Typically, you would apply electrochemical potentials to charged species. Now, I think with respect to the Fermi level, it doesn't matter. It's the same whether you say electrochemical. But of course, we have to align, when we talk about electrochemical systems, we have to align the Fermi level of the electrode to the Fermi level in the electrolyte. And then we have to talk about electrochemical potentials. So I think this is just a matter of nomenclature.
Yes, the electrochemical potentials at an interface are in equilibrium.
That's right.
That's the point.
Right. But I might tell you an interesting anecdote, a discussion I had a long time ago. Electrochemists typically look at the electrodes from the outside. So typically what they say is that the Fermi level changes if you have a dipole moment. This, of course, is just in principle a matter of the definition of the electron zero. But my background is also physics, as Andrew mentioned, and in principle, the Fermi level is a bulk property. It's a bulk property, and bulk properties should not change due to surface properties. So I also would prefer to specify a bulk property, which is the Fermi level, and then relate the issues to that. But this is just, I just want to alert you about a discussion also between electrochemists and physicists with respect to the levels and the absolute position of the levels.
Yes, I noticed that physicists and electrochemists have different terminology when it comes to chemical and electrochemical potentials.
And again, this makes this field very interesting. And I might also still kind of invite you to question the concepts. I'm also have moved from a physics department to a chemistry department. And of course, it takes some time before you learn the nomenclature. And especially, I must admit, electrochemistry is very complicated with this like of 20, 25 different definitions of potentials. And some potentials are local potentials. Some potentials are kind of potentials in the sense of chemical potentials, which should not depend on the position. And you really have to go through this and ask questions all the time. Please.
Yeah, true. Thanks.
Maybe I can also quickly ask a question, Axel, on top of the previous question. I think this is really a good point. So, so far you've been discussing the work function variation upon absorption or in liquids. But let's suppose we have a lot of different materials or different metals, and we want to predict their electrochemical behavior in one way or another. Can we use the work function of a bare metal to predict anything about it, or because there are a lot of still works published where people still use it from time to time again. So maybe you can comment on that.
I mean, you see, this is in principle a question about, it's I would say also more related to heterogeneous catalysis and reactivity concepts. What determines the reactivity? And often reactivity concepts are related to adsorption strength. And typically the reactivity concepts, you have the work function is not a direct component. Especially with metals, you would rather use the D-band models and so on. So the work function is an important property. And of course, it tells you in principle how far electrons spill out and so on. But this is also directly related to the electronic structure of the metals. So to make a long story short, I never argued in all my papers so far as reactivity is concerned with work functions. Rather, you should look at the electronic structure of the metal atoms or the atoms at the surface. Of course, on the other hand, I must admit that I like the work function very much because this is observable. You also find that often you find that reactivity is discussed with respect to local charges. But local charges are no observable. And also there's no true definition whether an atom is positively or negatively charged when it is embedded in a solid, because where does the atom end and the next one start? Of course, you have all these charge partition schemes. You have Mulliken charges, beta charges, and they are helpful to find trends. If the charge increases, then it increases. But the absolute values, you should never taking them literally. They do not make any sense.
Well, great, thanks.
To a certain extent.
Yeah. Any other questions?
I have a question. Thank you very much for the very interesting presentation. A basic theory question. You stressed out that thermodynamic energy does not depend on a path, and so it is not like necessarily directly connected to the underlying electrochemical process.
That's right, yeah.
So I'm just wondering, at which point then electrochemistry kind of comes into play? So when we should take into account, like, is it through the open circuit voltage, like the difference between the Fermi level of the cathode and anode, or like through something else in the system?
Of course, I tried to emphasize this point, but of course the battery is still an electrochemical object. And in principle, the electrochemistry comes into the play through the fact that you introduce an electrolyte. And in principle, I mean, if I might put it a little bit kind of sharply, the poor electrons, they can't leave the electrode because the two electrodes, the cathode and the anode, or the anode and cathode, are connected by an ion conductor, which is supposed to be an electron insulator. So they have to take a detour. And this is, I mean, in principle, the working principle of the batteries. The poor electrons would love to recombine with the cations in the cathode, but they can't do. And only when you close the outer circuit, then the electrons find a way, and then they happily go there, do the work that they're supposed to do, and then recombine with the cations, typically in the cathode. And I think this is the basic principle of batteries of this lithium-ion battery type. Of course, there are also, and to be precise, there are many different battery types. There are also some battery types where you have some reactions in the electrolyte. But this class of batteries, like lithium-ion batteries, are in principle rather simple. And in the very moment, then you have the electrolyte in play, and so on. Then you, of course, need to also involve electrochemical concepts. But still, the basic process, or you need to have a driving force. And maybe this is also a physical, the electrochemists would say, okay, the cations have a higher potential in the cathode, and that's why they go there. But I think this is not a very obvious way to understand this. Why do the lithium cations why do they like to go to the cathode? and you need a driving force, and the driving force is in principle the energy gain of the atom upon insertion into the cathode. And I think this is important also for fundamental understanding of what happens in this.
Yeah, thank you.
Any other questions?
Professor Axel. Okay, I have a question. You were mentioning regarding the common nomenclature of using HOMO-LUMO gap to understand the electrochemical stability window of the electrolyte.
Yes.
In one of the slides. So, what could be the alternate way how we can get an idea, at least for the academic purpose or for a teaching purpose, how we can explain that in a much better way? Do you have any better comments for the same?
So, I mean, the principle, this is the slide that you've referred to.
Yes, exactly.
What I would, I mean, to make my life easy, I said, just please have a look at this paper. Maybe you have the time to write down this, where this is very described in very much detail. And I also please consider just the example of water. And you see, this interesting point is that I heard some electrochemists saying, John Goodenough is a physicist, that's why he doesn't understand electrochemistry. Really, the HOMO-LUMO gap does not matter, as described in this paper, and where you at least see this very, very prominently is water. Because water has a HOMO-LUMO gap. Of course, it's not a crystal, but so you could estimate it's like 8 eV. But the water stability window is much, much, much smaller. It's only 1.23 eV. And this is also the problem in batteries. We would all love to have batteries with water as the electrolyte. But a lithium-ion battery has a voltage of 4 volts. And water immediately would decompose in such a battery. And that's why it's in principle, in a simple word, it's the redox potentials. And in fact, again, I repeat myself, please have a look at this paper here, where this is explained in much detail why this is so. Okay.
Any questions, or can I ask the last question? And anyone still? No? Okay. Axel, I have still one more question related to one of your, I think the first part of your talk, when you showed hydrogen atoms moving on top of platinum underneath the water layers.
Mm-hmm. Just moving.
So in general, when you do these calculations, how would you estimate the accuracy or the adequacy of the description of hydrogen diffusion? Because hydrogen is, I mean, it's a proton pretty much in this case. And so whenever you have protons moving, I mean, there are many different ways, right? There are path integrals and other approaches to calculating it. But in this molecular dynamic simulations, would you say that this is extremely accurate compared to other methods? Is the most accurate way to describe the hydrogen diffusion?
I mean, you raised a very interesting point or important point. I would not agree with you that it's a proton then anymore. The very moment it comes down here on the surface is then it's a hydrogen atom adsorbed on a metal surface. And then for every practical purposes, it's in principle, the interesting thing about hydrogen also that it's just like a metal bonding. It's a proton embedded in the electron sea of the metal. And this is where in principle DFT is rather good for. And to be honest, also, I can tell you, sorry about another anecdote. My PhD supervisor once was thinking of checking whether the adsorbed hydrogens are protons or hydrogen atoms. And his suggestion would be to look at quantum statistics. Because if they were protons, then they would have a spin, there would be spin 1/2 particles. If they were hydrogen atoms, they are not spin 1/2 particles. Unfortunately, nobody ever did these experiments, but I think this doesn't make sense. They are, for every practical purposes, they are adsorbed hydrogen atoms. And in principle, for example, one can calculate the diffusion barriers and compare with experiments, at least in the gas phase. That's where they're pretty good. platinum in principle also, I mean, now, sorry, that it's an interesting beast, because hydrogen has a very, very low diffusion barrier on platinum. This is already in gas phase, so, and surface scientists know about this. And this is also to the fact that the absorption energy between the top side, the bridge side, and the hollow sides only differs by something like 40 millieV. And this, in fact, leads to quantum delocalization. So this is also very well known from surface science experiments. And so when I first saw these movies here, that they move so freely, my immediate response was, aha, okay, so the water doesn't matter. It behaves like hydrogen on the clean platinum surface in ultra-high vacuum. And I would guess, and of course, this does not really answer your question, but I would rather feel confident that this is well described, because, and again, this is in this point, I would be rather firm. Once you have an ion from solution absorbed on a metal surface, it's no longer an ion anymore. It's an adsorbed species. You can calculate dipole moments, and of course it can be still have some preferential, and this is why, and then you could then determine the work function, at least for the gas phase species, and then you find still a dipole moment there and say, oh, okay, it might be still a little bit negatively charged, or it might be a little bit more positively charged, but certainly the language of cation and anion is no longer appropriate in my opinion. And one has to, and of course, I know also that the electrochemists like to use these concepts when discussing adsorption. But in my opinion, they are misleading. Sorry to be so.
No, this is really, I think this is one of the most important points, actually, because there is a big discrepancy between the two lines of thoughts, I would say.
Right. I mean, again, I mean, as long as they are in the electrolyte, of course, it makes very sense to say it's a proton, it's a cation. But the very moment they are bound on the surface, they are embedded, or even it does not only apply to hydrogen, it also, it's the same thing with chloride and so on. They are just adsorbed on a metal surface, and they are new species. They are no longer cations, anions, but there are new now adsorption complexes. And it doesn't help to use this concept of cations and anions. I mean, or it's too easy just to think in terms of these easy concepts. It's no longer ionic bonding. It's really it's metal bonding.
Axel, but this is about platinum or the metals, the materials with a lot of electrons at the thermal level. But let's suppose we look at an oxide material or a partly semiconductor material, so a material that has a small density of states near the thermal level. In those cases, the situation changes, right? So your absorption strength now is different. Everything is completely different, and we can't really approximate this platinum to whatever hydrogen or oxygen or chlorine interaction into those low density materials.
No, you're fully right. And I, up to like 5 years ago, also we really concentrated on metal surfaces. Recently, we have done a lot of studies also on oxide surfaces. In fact, this seems to be unrelated, but we have also looked at many oxide materials with respect to ion mobility in battery materials, and there's the same issue. Is an lithium ion that inserted into a spinel, is it still an ion or not? And I would say there, of course, you are fully right, they are no longer metals. But in principle, what is often replaced is that then instead of metal bonding, you also have a huge portion of covalent bonding. Of course, also, these are still, if you wish, man-made concepts. The distinction between ionic bonding, metal bonding, covalent bondings are just ways that we introduce in order to kind of bring some order into the complexity of bonding types. But there's never ever any true ionic bonding, any covalent bonding. Of course, if you have a diatomic molecule, homonuclear like H2N2O2, of course you say there is no ionic bonding because they are similar. But and also what we found is that in particular with respect to the so-called ionic mobility in electrode materials, this doesn't capture the truth. You have to include also covalent bonding. So this is a very, very important issue, and we have to check ourselves whether the concepts that we have, which often are derived from molecular bonding or pictures, are really appropriate to describe this fully. And again, as an easy way out, the world is never black or white. It's 50 shades of gray. So it's all these this different. There's never the one has to always check whether the simple concepts of covalent, ionic, and metal bonding are really appropriate.
Thank you. And maybe just as a side comment, as you can probably make it for hydrogen, not the hydrogen, but the proton diffusion. So when you do MD simulations of a relatively thick layer of solvent, of water, for example, and you have hydrogen diffusion there on the surface, but then you have proton diffusion in, well, slightly away from the surface. That proton diffusion, is it, so okay, hydrogen diffusion seems to be well described by the MD plus DFT, but what about the proton diffusion itself?
Yeah, I mean, you see, if you look at, I try to go with my cursor here. You see here also hydronium falling. So in principle, I mean, this is also relatively well described. And of course, you also, as I told you, whenever we, for example, we would add here one hydrogen atom, this hydrogen atom would immediately form an hydronium ion, and the electron would go to the platinum surface and then change the charge of the platinum surface. And typically also these functionals describe the liquid water properties rather well. And there are even now studies which use this RPBED3 functional that can also describe water properties in the regime under high pressures and everything else. So it seems to be that these GGA functionals pretty reliably describe both hydrogen absorption at the surface, where also the property of liquid water, including also this Grotthuss mechanism of proton transfer or proton diffusion in water. So I up to now, I would not see any reasons to think this is not a proper description yet. There's another issue, of course, which I haven't touched. This is still classical simulations with respect to the nuclei. So you, of course, could discuss nuclear quantum effects, which are there when you discuss hydrogen, but this is a full new story. And I could give a next talk about that if you wish.
Yeah, I think this is actually one of the potential talks that we're considering now. Yes, so the quantum mechanical effect from hydrogen.
Can I
yes,
add one comment? My name is Anonas Lucis. Regarding the adsorbed hydrogen and proton, actually from the experimentalist point of view, I would say the adsorbed hydrogen is always in dynamic equilibrium with the proton in the solution. So principally, it can desorb as a proton, but at the same time, if you stay at the constant potential, new hydrogen will adsorb on the other platinum atom, which is not necessarily neighboring atom. So principally, this diffusion model, this is something, yeah, it is nice, but it does not consider that the adsorbed hydrogen can easily desorb as a proton, and simultaneously the proton can readsorb on the other atom of platinum. So principally, this is always dynamic coverage of hydrogen.
And you're of course fully right. I mean, we have here a trajectory of a couple of picoseconds, and of course, very easily this hydrogen atom also can bind to an other water molecule. And in fact, we also did simulations of this and found some, so to say, events where hydrogen atoms would attach to a water molecule or hydronium and go on. And this was within 7 picoseconds. Of course, you're right. This is a fully dynamical object. And you also, if you remember, not only about hydrogen, also the simulation with the water layer, how dynamically the water molecules are. There is no single water molecule staying for a long period of time at the surface. They're constantly exchanged. So you're fully right. This is a very, very dynamical system where everything changes all the time.
Thank you.
May I ask a question?
Sure.
Thank you very much for your excellent talk. I was curious, when you consider the implicit solvent model, what would be the best approach to actually account for the modified interfacial layer? Because when I think about kind of assuming modeling the solvent, then you would think that, you know, it's an average picture of how bulk electrolyte behaves, but then interfacial layer is always very different from the bulk property of electrolyte.
No, thank you very much for the question. I kind of forgot to make this clear. I would suggest the following recipe. You can't use ab initio molecular dynamic simulation to look at equilibrium structures, because you would need to take too many different trajectories. So my recipe would always be first doing a calculation, as I just explained here, doing this computational hydrogen electrode, and as a guess, and then from this computational hydrogen electrode here, you would get a Pourbet diagram. And then you say, okay, I want to do a simulation in this regime. Okay, here I have to take into account the sulfate layer, and here I have to take account the clean platinum surface. And then in the second step, you might then reconsider again. Now I want to look at processes, reactions, maybe the water structure, and then I would add the water. But of course, in order to kind of find the structure, you have to do many calculations. And if I go back here to this particular picture, if in this particular system, we looked at 118 different adsorbate structures. And of course, we can't do this with really explicit water molecules. So this would be my kind of recipe or suggestion. The first step is look at the structures, but in a more, they are surprisingly stable. Of course, I made this point that with particular to the sulfate, you need to take into account water, but only this once here, then, or you could get away with implicit solvent. And there you would first scan the possible adsorbate structure. And then once you have done this, then you can this kind of answer your question to a certain extent.
Yes, it did. Thank you very much. And I have another question. In the first part of your talk, you mentioned that after certain number of picoseconds, the water layers are fully disordered, and that the models of the double layer should actually, I think you had this from a picture from Wolfgang Schmickler book about disordered water molecules. But I think if you consider dielectric permittivity of water, it is frequency dependent, and it also depends on the number of degrees of freedom of the water molecules. And if we apply this to calculate the, do you still hear me?
Yeah, I hear you,
Yeah. So then if you have this many degrees of freedoms and you apply the values of the dielectric permittivity of water molecules, depending on the number of degrees of freedoms, I think it will be much lower if it is more constricted. And if you compare the experimental values of the dielectric capacitances, and if you apply very simple approximation using Helmholtz model, then from this it would look like that the dielectric permittivity should be on the lower side, meaning that actually there is quite a bit of structure to the water molecules in the interfacial layer.
I see your point. I mean, this is a very, very interesting point. You see, this is when I was brought up, and sorry to as a young student, and I had classes on electrodynamics. Jackson, I was taught that dielectric constants are a mesoscopic principle. There is no local dielectric constant. Of course, this is now again an easy answer, but I think I think one has to really find out what one really measures. What do you measure if you have some permittivity? Of course, I know also that you can measure them frequency dependent and so on, and I'm no really expert in it. But I'm kind of skeptical whether these permittivity concepts are really so much relevant. And also, I mean, of course, you are true. I mean, still these water molecules at the first layer, of course, they can't move that freely as inside of the water, liquid water. This is just a purely geometric argument. You have the metal atoms and so on. So I don't know. I certainly would agree that they can't rotate as freely as a water molecule in liquid water, but this might be just a geometrical constraint. So I would not say that this doesn't mean that still the structure is disordered, but every single water molecule can't rotate as freely as a water molecule in the liquid water. And I think this would then maybe combine these two pictures.
Yes, yes. And most probably once you introduce cations, they also constrict the orientational freedoms of the water molecules even further.
You're fully right. Of course, and since water is so dipolar, they will be oriented, and then of course again they can even move less freely than without the presence of charged objects. No, I fully agree. Maybe there is. I think there might be no contradiction between these two pictures.
Thank you very much.
Okay. Any other questions from the audience? Okay. So if not, then at this point, let me thank our speaker. It was really, really great talk and even greater discussion of the talk. And so everyone, I'm really thankful that you stayed until the end. Well, it was almost 2 hours now. And so I hope to see you next time. Thank you so much.
And let me also say that I really enjoyed giving the talk and the discussion. And again, thank you very much also to you, Andrew, for setting up all this. Thank you very much.
Thank you.